In this video, we're going to continue to look at graphing nonlinear functions, starting with this guy. F of x equals 1/4 times the quantity of x plus 3 squared. So again, you look for the key markers that tell you what the shape is. So I see the square right here. That tells me that I have something that is a parabola, like this. And then look to see what I've done with this shape. How have I shifted it up, down, left, or right? Is there a stretch or compression? Did I reflect it? Well, I see a plus 3 on the inside. So inside is a horizontal shift, opposite of what I see. So that means instead of going to the right 3, which is what a plus 3 is, I'm going to go to the left 3. Notice that there's nothing being added or subtracted out here, so there's no vertical shift. But I do have this 1/4 in front. And this 1/4 means that I'm going to have either a stretch or a compression. Now, since 1/4 is something that is less than 1, it's going to give me a compression. So it's going to take this parabolic shape and it's going to just crush it down. So instead of being able to grow as steeply as it normally does, it's going to be growing at 1/4 that rate. So this tells us that we have a compression. Compression by a factor of 1/4. Alright, so let's see, we got to go to the left 3, so I'm going to put my vertex to the left 3 right here. We're going to draw a new set of x and y axes. So there's my x. And there's my y. And I'm just going to mark these guys off. So this is going to be my 0, 1, 2, 3, 4, and so on. Okay, so these are going to be my new x values. These guys are based off of where my new vertex is, so I don't want you to say, oh, but that was negative 2 and negative 1. I don't really care. It's where are you relative to that new origin. So think about the key values that we have here. So you've got x, and then when you have f of x is equal to x squared, what do we have? So you plug in 0, you get 0. You plug in 1, you get 1. 2 gives you 4. 3 becomes 9. 4 becomes 16, and so on. But now we want to look at what happens when I apply that 1/4. So if I do 1/4 x squared, what happens to all these guys? Well, this becomes 0 divided by 4, which is just going to give us 0, right? So that 1/4 is going to divide all of those output values by 4. 1/4 is, of course, just 1/4. We're going to take 4 divided by 4 to get 1. 9 divided by 4, so that gives us the mixed number 2 and a 4th. And then we have 16 divided by 4, which is 4. You might wonder, why are you wasting this time? It seems like I'm wasting my time, but it's to help me get the nice points for graphing this. So 0 gives you 0. When I go 1 unit out to the right, you got to think about what you're doing here. You're going to square it because it's the squaring function, but then you've got to multiply times 1/4. In other words, divided by 4. So 1 squared is 1, but you're going to divide that guy by 4, so you're going to have 1/4. 2 squared is 4, so you would have been up here, but now that you have that 1/4 factor in front, you do a 1/4 of that and you have 1. So you can start to see where there's this compression. You have this normal pattern right here, but you're doing a 1/4 of that, so it's going to be considerably flatter. Okay, see how much flatter it's going to be? 3 squared would be up here at 9, but you're doing a 1/4 of that, which we did the math, that's 2 1/4. So 2 1/4 right here. Normally 4 squared would be 16, that's way off the chart. But I'm taking that 16 and dividing by 4. So we end up with that guy right there. And you can copy these on the other side. So there's the 1/4, 1, 2 1/4, and 4. But we need more points, right? So if we kept going here, think about what would happen with 5. So 5 squared, sorry, fingers are always in the way. 5 squared is 25, and then 25 divided by 4. Let's just add that down here. So 5 will give us 25. and I do 25 divided by 4, and 4 goes in 6 and 1/4, which is going to be right about there. And of course you can copy that on the other side as well. I bet we can go one more, and let's go to 6. So let's see, 6 squared is 36, but then we have to do times 1/4. So 36 divided by 4, 36 divided by 4 is 9. So it's going to be up there. And so now we have a lot of points here, a lot of nice pretty points that we connect to form our parabola. And let's compare this to what the original shape would have been without the 1/4. So I'm going to dash this here in red. So this is normal x squared. And this is what happens when you do 1/4. Now, I guess really it should be, x plus 3 squared, but you just want to get you to see the difference between the normal squaring shape and if I put a 1/4 on that. Okay. So yeah, you can definitely see there's a compression, and that's one of the things you need to understand. When we talk about a stretch or a compression, it's going to be in a vertical sense. So you're taking this parabola and you squeeze this down, and he starts to get wider. He can't grow as fast. Okay, let's try some other examples. We've got a couple more. Starting with this one. F of x is equal to the square root of x plus 5 minus 6. So right away, I see the square root. And the square root is that half sideways parabola. Something that looks like that. So you've got to know your shapes so you know what your key points are. Looking at what I have on the inside here, I see a plus 5 on the inside, so I do the opposite of that. That means I'm going to go to the left 5 units, and then I've got a minus 6 right here, so that's on the outside. I do a vertical shift, exactly what I see, and that means I'm going to go down 6. You'll notice there's nothing in front of the square root, so there's no stretch, there's no compression. It's just going to be our normal square root shape, just in a new location. So we go to the left 5 and down 6, and that's where we're going to start. And here we go, drawing our new x and y axes like we've been doing. You've got to understand your key values for the square root function. You've got 0, 1, 2, 3, and you skip over to 4 because you would be trying to plug in perfect squares into the square root. So the next nice number you plug in would be 9, but we're measuring that as 9 units from this new origin. So 4, 5, 6, 7, 8, and 9. Think about what the key points would be. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. So it's the same key points that we would have had for the normal square root. We just took these points. We took this guy, we shifted to the left 5 and down 6. So there's the new guy. And now we just connect the dots, drawing a nice sideways half parabola like that. And that's all there is. If there had been a number in front of this like a 2 or a 3, you would have been stretching this vertically. So if I had a 2 in front, a 2 would have been taking these guys and doubling this. So this would be up here at 2. Instead of 2, you'd be up at 4. Instead of 3, you'd be up here 6 units. If it were 3, you'd be tripling all those values. It's just that simple. Not a whole lot to it. And you see that we don't have to recreate a new t-table of values. Just know the key values for the regular square root function and build those points anew from this new origin. Okay? Alright, one last guy right here. H of x is equal to negative 2 times the absolute value of the quantity x minus 5 plus 3. Since it's absolute value, we know that we have a v shape. Now we have some stuff going on inside the function, so I see the minus 5, which means I need to go to the right go to the right 5, and it has nothing to do with the absolute value. It has everything to do with the fact that the minus 5 is inside your main function, inside your parent function. And then I've got plus 3, so that's outside. Vertical, I'm going to do exactly what I see there. So that means I'm going to go up 3 units. But don't forget about that negative 2 that you see in front. This negative 2 means that we will reflect. We're going to reflect across the x-axis. And the 2, since it's greater than 1, means that we're going to have a stretch by a factor of 2. And again, for absolute value functions, that's really quite simple because you can use that negative 2 like a slope. So we'll imagine that being negative 2 over 1. So start off by going to the right 5. So to the right 5 and up 3, like that. That's your new vertex. And we use that as our new reference point, our new origin, if you will. And so we can imagine these being our new x and y axes. We've gone to the right 5, we've gone up 3. I don't need that information anymore. I now use the negative 2 coupled with the shape to get everything else. So the negative 2 means from here you go down 2 over 1, down 2 over 1, and so on and so on. You do the same thing over here on the left side to get the other half. We go all the way to the edge. And since we have these straight sections here for the absolute value, might as well use our straight edge. And the same thing over here. Just like that. Now, I do want to point out something with one of the problems that we did at the beginning of this video. Here, I can use the negative 2 like a slope because the absolute value is made up of straight pieces, right? At the beginning of this video, we had 1/4 in front of a squaring function, and you'll notice that I was unable to use that 1/4 like a slope. I can't go up 1 over 4. It's not going to line up. If you go up 1 over 4, up 1 over 4, then at that point you're not graphing something that's quadratic. You're graphing an absolute value or something that's just a line. But the square tells us that it's a parabola. And so since it is not made up of straight pieces, we can't use that 1/4 like a slope. But we can connect it back to what we have seen with slopes. So if this is a slope of 1, a slope of 1/4 is going to be less steep. And that's exactly what you see here with this shape. You take all of these normal points and you divide them by 4 to get that compression. All right, so see what you guys can do on your own.